Myself, my name is Kartik. I run the systems engineering function for VAST globally. That's our pre-sales organization. So I get to work with a lot of customers, and I'm going to be talking to you about a lot of them and what they do today. I also have some live demos, which I'm going to be doing, fairly short ones, but ones that will give you a feel for how some of the technologies actually work. Not to worry, I have promised the demo gods that I will sacrifice a fresh coconut just to appease them, so they all work as planned. Obviously, being a Hindu, I can't sacrifice chickens, otherwise my mother is going to disown me. So I'm going to go forth and stick with coconuts at this point, right? So wanted to give you a quick feel for why it is that the architecture that we have is actually so effective for working with the GPUDIRECT technologies that CJ talked about. So the basic VAST cluster, northbound, we expose ourselves through file and object protocols. So we support NFS 3 and 4 and SMB and S3. But the most important thing, of course, here is that we also use RDMA as an underlying transport layer. Like CJ explained, the trick is to get the data from the storage directly into GPU memory, thereby bypassing system memory and the CPU complex. And when that happens, then any kind of application at that layer is able to directly access the data into GPU instead of having to move it in there. That gives a lot of performance benefits over here, and this is what makes it happen. Now, this worked out of the box for us. I was working at the NVIDIA labs when we were testing this initially. It took us 6 hours to get it working because we already supported NFS over RDMA. And it came as a very pleasant surprise to all of us that it actually did what it's supposed to do. But then we did some enhancements to it as well, so we could vector the entire performance of the cluster to a single client. So we said, let's hook up a big machine like a DGX A100, which has 8 200 gigabit HDR NICs on it, and say, can we really saturate these things? And the answer is yes, of course. But before I go there, let me just show you very quickly how these things actually might work. What I have here is a little GPU server. It's actually pretty small. This has a T4, and the reason I chose this deliberately is to show you that GPUDIRECT is not just something exclusive to big systems. It'll run on any GPUs. Basically, it's part of CUDA right now, and long as you have a more recent version of CUDA and the GPUs are compatible, this is going to operate. This is one of the smallest systems that you can imagine. Nevertheless, it works extremely well. So what I'm going to do is to run a little script over here, which basically is running GPUDIRECT. And here the data is going to go directly into the system memory at this point. So if you look at our UI, you'll see that I'm getting, I'm starting to ramp up the IOs on the system for the UI, and we get about 10.6 gigabytes a second, between 10 and 11 gigabytes a second. Let me tell you one thing. That itself is a miracle in the world of NFS. All right, NFS typically gives you 2.2 gigabytes a second on a good day, and the sun is shining bright. But in this case, we're like well past even what something like NConnect would give you. We're going to line saturation for the system. This machine has not just a T4 GPU, it has a CX6 NIC on it. This is about line speed as far as that thing goes, right? And the data is going directly to GPU in this particular case. Now, if I go and say, okay, let me now look at something else, let me now look at a different data path where I would actually not go through the GPU. What I'm going to do is to go through the bounce buffer. I'm going to take the same data and I'm going to move it into CPU and system memory, and then I'm going to go down again to GPU. Now, I forgot to mention that I wanted you to watch the top one. If you notice, if you recollect, I'm running HTOP on the top. It just shows the utilization of the cores. It's fairly minimal in that case. Watch what happens when I actually run this, run this thing through the system kind of memory. So you'll see that the CPU utilization basically lights up like a Christmas tree. Why? Because now all the work of moving the data is actually going through the CPU, and you're eating up all that stuff. And that's really what starts to hurt you. So there's a huge buyback from a CPU utilization standpoint if you move directly into GPUDIRECT itself. Now, the astute viewer will notice that only alternate cores are lit up. Not to worry, it's because there are 2 NUMA domains on this machine, and the NICs are connected to one NUMA domain, and the GPUs are connected to another one. Hence, you're only seeing half the cores light up. But the basic thing is that this is very, very effective when it comes to moving data. Now, we have, of course, taken this pretty much to an extreme at this point, and we are able to now look and say, when we did the testing at NVIDIA labs, this time it wasn't a puny little server with a T4 and 1 NIC. This is 8 HDR NICs, 200 gigabit NICs. We were able to get an astounding 162 GIB in the system. On a system which was like theoretical capabilities of 200 gigabytes a second. This is about 175 gigabytes a second, single mount point, single client. I'm going to wager that that's about 20 times what anybody else in the history of mankind has ever done for NFS at this point. And why? It's because we are able to take all the power of the cluster, move it directly into GPUs. And this limit you see about 46 gigabytes a second, that's an internal bus bandwidth limit between system memory and GPU memory. And this is why this is so effective. Okay, so now I'm going to switch gears a little bit and start to really talk about some of the use cases that our customers have used us for. Some with GPUDIRECT, some with GPUs. To me, GPUs, AI and machine learning and deep learning is not a vertical. It is a horizontal. It is universal across the board in almost every single industry that I have seen. Life sciences is no exception. And one of the hottest fields that we've seen right now is this area of structural biology. Everybody thinks of genomes when you think about life sciences research, but actually the hot thing right now is proteins and protein structure. Proteins are exceptionally complex beasts. As you can see over here, some of the pictures, they're strings of amino acids, but you can fold them in any way, shape or form. And this gives rise to beautiful and complex structures, which are critical to understand new drug discovery, what happens when you embed molecules, or how do these things interact? Like, for example, with COVID and the COVID spike proteins that are coming up. All of those really need techniques which go well beyond what a basic genome sequencing can do. And as a result, there are some new techniques which have come up over here, especially in the area of cryo-electron microscopy, which are used to look at the structure of very, very small parts that make up life. I'm not going to go into detail into what cryo-EM techniques are, but suffice it to say that it involves supercooled water with proteins in them and electron beams smashing them and capturing a lot of data coming out of them. And a lot means, I mean a lot. These things generate petabytes and petabytes of data every year, and therefore people need to store it, people need to analyze it, and a lot of the analysis happens in GPUs. Complex, time-consuming, expensive. But there's been another innovation in the deep learning field, which I think is super cool. And this is to use predictive analytics to be able to predict what protein folding structures are going to be like. And this is an innovation which came from Google, from DeepMind. For people may have heard of this thing called AlphaGo. AlphaGo was a machine learning program to play the game of Go. It trained for 8 hours by playing itself, and got so good that it was able to beat the world champion at Go right after those 8 hours. These fine people at Google turned their mind to a protein folding problem and came up with a model which is literally capable of having 95% accuracy in predicting what the protein structure is going to be, given a string of amino acids. And that means that the advances of science here are immense. People believe that this actually should get the next Nobel Prize. We do work in both areas, and the work is phenomenal. In the area of cryo-electron microscopy, this is one of our most popular use cases in structural biology. Shown here is actually a talk which I actually co-presented at the last GTC conference at NVIDIA. This is done with Dr. Sliz from Harvard Medical. He's associated with Boston Children's Hospital. They do extensive amounts of work in cryo-electron microscopy for structural biology. And he has just recently published a paper on the Delta variant for the spike protein in COVID. And that's all done with us. we do very well in this because we do as good as local NVMe drives when it comes to that. After all, even though we're NFS, we are one of the fastest platforms there for this kind of I/O. So we work very efficiently in this space over here. ALPHAFOLD was even more interesting. A large research university on the East Coast called us very excited one day and said, we just downloaded the latest version of ALPHAFOLD and it rocks. And we're like, rocks compared to what? It rocks compared to the parallel file system that we're running it on. So we were curious and we went and got ALPHAFOLD and ran it on the DGX that we had in our lab. And what we found was that the performance we got was as good as local NVMe drives, but the parallel file systems would give performance which is 5, 10, 15 times worse. Reason is actually very subtle. Many people look at these kind of benchmarks and say that bigger is better. How many gigabytes, hundreds of gigabytes do you get, or how many millions of IOs you get is going to decide how well an AI job is going to run. I beg to differ. Underneath this, basic reason why it slowed down on other systems other than us is the fact that these use a lot of mmap calls. So for those not familiar with mmap, it's really done at the level of Linux. It maps shared memory pages to the data. But the data is not fetched into memory. It's a technique to minimize memory use until there's a page fault. That is, the application requests the data, which says, give me the data from this block, and then it goes and fetches it from the disk. So the storage system looks at this as a storm of 4K IOs, because that's the page size for mmap. And that overwhelms parallel file systems, because parallel file systems were built for large block sequential. And they have a complex metadata model. So when they get hammered with small block random, they kind of get in knots and have a real hard time satisfying it, because they go and prefetch stuff, which is unnecessary, and just increases the overhead on the system. We don't know any of that. Our metadata model is not one which is distributed. Any of the containers that we have can see the entire namespace, both for data as well as metadata. This gives us some phenomenal performance for this kind of stuff. Switching gears, here's another very cool use case. This is truly, we think, like, again, to CJ's point about visualization, this is about data capture, about video capture, volumetric analysis. So you look at stadiums and you look at concerts and things like that, you have dozens, tens of cameras all over the place, capturing data from all angles, allowing you to synthesize real-time video. To do all this, this work was actually done at Verizon, who's a customer of ours. And the amount of data you ingest from these cameras is so great, and the amount of processing that's needed requires a very complex set of a very complex pipeline for GPUs. So that again is a field which is great. So this is just a quick depiction. They also talked about this at GTC as to what their pipeline is. So from capturing to generating the point clouds to ultimately going through the pipeline processing over here to get to the final result, which ultimately is broadcast. So the secret here was, again, how do you move data directly from the cameras to the storage through the GPUs? To the rescue, GPUDIRECT. Perfect kind of technology. They expect a speed up of 10x compared to what they're doing, and they're going to be writing 250 terabytes of data over here. So these kind of use cases could not even be thought of at one point. And the complexity of the analysis that needs to happen is immense. So this is the kind of stuff that we are so excited about. Another field, the field of medical imaging. This work was done at the Martinos Center. Martinos is a collaboration between MIT and Harvard. And they basically combined together, they focus on medical image processing again. Again, GPU intensive work. They were one of the earliest DGX A100 customers. I believe they were the first. I wouldn't be surprised if they are. They brought us along with VAST as well. Great economic impact, because the VAST systems were affordable enough that they were able to save money and get themselves one more DGX with the money that they saved from the overall budget. So we think we've helped NVIDIA there, but definitely we helped Martinos over there, because they needed the processing power to be able to do this. This particular case, they did radiology images. They did radiology image analysis to be able to look at lung function for COVID patients over successive days. Now, what that lets people do, lets the attending clinician do is to figure out when a patient might need an intervention and need a ventilator or something like that. Back in the day when Delta was running rampant, this was very, very critical. So this is not, of course, the only use case. They do MRIs, they do a whole bunch of stuff. All of these are heavy GPU-based workloads where they depend on technologies like FAST to be able to go forward with.
Can I ask you, most of the use cases that you presented are, involve a lot of throughput. So sequential reads of a lot of information. But actually, there are a lot of use cases where you deal with machine learning with very, very small files.
100% right.
And so what happens in this case? Because at that point, latency becomes a problem that maybe, can be.
You're absolutely right. But I will, one thing I'll tell you, when I talked about ALPHAFOLD here, this is not a high throughput workload at all. This is lots of small block random IOs that are going through the system, but I hear your case.
And that's also the result of what mmap does.
What mmap does over here.
It ends up being IOs of the size of the memory access into the mapped memory. And so they end up being very small and random.
Okay.
Yeah. The way that I think about it is, we've kind of presumed flash in this conversation, right? And the assumption here is that random access media is at your disposal. And an accumulation of small files becomes throughput when you're blasting them into a machine quickly enough. So these are on average 100 kilobyte or so requests that you're pumping into a system in the gigabytes a second range. So they're very small files, but there's just a lot of them going into the GPUs.
Yeah.
No, yes.
And yes, so we gather those. So even say natural language processing problems, for example. So we've done a lot of work with things like BERT. Data is small, but the compute and GPU requirements are large. We work perfectly well in that as well, in all these kind of scenarios as well. So we are by no means limited to purely large throughput systems. Our real value proposition at VAST, to be honest with you, I mean, I love to show off numbers, but at the end of the day, we are valued because we scale linearly and easily. We are valued because we are all flash. You need the democratic access to all the data at all times. We're valued because we're super easy to use. And we're only industry standard protocols on the front end. And lastly, for an all flash platform, we're the least expensive, which is out there. You put that combination together, you get the rest of the performance for free when you got that much flash. You don't even have to worry about it. We get NVMe level performance almost every single time in lots and lots of cases, and I'll show you a couple of examples too. So this again is another kind of model. This is the climate segmentation model, which is actually hosted at NERSC. I'll give you an example why exactly this is so interesting, because this segmentation model is part of MLPerf, which is the sort of the gold standard for being able to do benchmarking for GPU-based systems. Highly studied. This is used for both training neural networks as well as for inference for neural networks over here. Just to give you a quick idea of what I'm about to show you, a piece of this, and this is in the deep learning framework PyTorch. This has a component called PyTorch loader. And what the loader basically does is, and this is the kind of the way all loaders would work, there's data on the disk, and then you consume it in what's called a batch. So it's never a big sequential I/O. It's not a big, huge sucking sound of data going into the GPUs. It's always small batches that get loaded and then loaded in a pipeline and then get processed after that. So at that point, you basically do this, random picking of the data, you build it into batches, and you move in here. So one of our customers, NERSC, who actually hosts this data, did some testing to look to see how well do you do really when you have to load, say, 0.5 terabyte, data set into a system with 8 GPUs. To their delight and to our delight, they found that we were as fast as local NVMe drives when they did that. Similar situation moving an HTF5 file also through PyTorch loader. Once again, they said that, hey, you are significant. You're as good as local storage. Now, yeah, they compared us to a scratch parallel file system, but it's hardly relevant. I mean, my baseline is always, am I as good as local NVMe? And this is, and this is very, very powerful because this is the way we operate. It's not about huge amounts of data, but this is about very specific actual business problems being solved when we start to work with this. Inference numbers, this actually was the analysis, thanks to Thorsten Kirst, who helped us a lot in getting some of the data. He ran some simulations, again, with the DeepCam data set and the DeepCam model. And for inference, they were able to see anywhere from 3.6 times to maybe 3.2 times, depending on what the batch size was for moving the data in and processing it. And this is through the entire deep learning pipeline that they were able to do it. This was a GPUDIRECT. So the effect of GPUDIRECT is dramatic in situations like this. For training tends to be more CPU and GPU intensive, and therefore the gain is not as huge. But nevertheless, the combination of the two makes it a perfect type of technology to bring both VAST and NVIDIA together to be able to do this kind of stuff. So I'm going to now end at this point, giving you an example of how this actually give you a feel for how a real, to demonstrate a piece of this using one of the frameworks, DALI. DALI is a data loader and an image augmentation framework. And what it does is it allows you to not just load the data, but to introduce distortions into the images that you load, because that increases the accuracy which you get from training, right? So to do this, what I've done is to actually build a little thing here, a little bit of Python here. So bear with me. Everybody told me don't show code, but I am like just not that kind of guy. So let me, I have to show at least a little bit of code. It's really not that bad, right? So there's some initialization that I do. And then what I do is I define two pipelines. The first pipeline is actually the DALI pipeline, which actually opens files and loads them into memory. And then the next pipeline, I actually do an operation on the images that I just loaded. So if you notice here, in this pipeline, I defined that the device to use is a CPU. So the data is going to get loaded into CPU. But then the operation that I'm going to do with this, which is just a horizontal flip of the image, I actually do on the GPU. i.e., if you look at the data path, data moves from storage to CPU and system memory. And then for the flip operation, it's got to go from system memory to GPU. And then I actually flip the image. So this is very typical processing that you would do over here. So without any further ado, let's run this and see, shall we? So it's pretty short, and I basically open up a small data file. I have some MRI images here. And as you can see here, these are images of the knee, of the human knee, 4 MRI images. It's a small batch I'm looking at. And the operation I did was to flip it. So I've shown you the output before and after as well. Note the time that it took to do this, about 0.65 seconds or so, right? And this was using loading data into CPU and then doing the flip in GPU. Now I'm going to do the same thing, except it is slightly different in the sense that this time I'm going to load the data directly into GPU. This uses GPUDIRECT, right? This framework, DALI, the NumPy reader, NumPy is just a format for these images, uses DALI, uses GDS. So I'm loading data directly into GPUs. And then I'm going to do the same thing I did before, which is I'm going to flip the image, except this time, the image is already in the GPU. I don't have to move the data from CPU to GPU. So let's go and check this out. Let's see what we get over here. So restart and run all. And you'll notice that pretty much the same thing happens. And the output is pretty much the same as it should be. We expect the same outcome. However, look at the time. It's half the time it took for the CPU leg, right? This one took 0.65. This one is like running at 0.33 or so. This, in fact, is the reason why the workflows that I showed previously with DeepCam, et cetera, show this enormous gain for inference, for training, et cetera. All the workflows that I showed for Verizon, all of them basically work out in this fashion just for this reason.
I think the thing to kind of consider is the number of parameters that need to be kind of applied when you're building a new model, right? So we're talking about 0.3 seconds here, but multiply that by 200 billion.
Correct.
And then that's how models are being trained today.
Exactly. And I'll tell you, from the data scientist standpoint, it's all about time to iterate, wall clock time, right? They basically, if I double the speed of something or I triple the speed of something, that means my time to value, time to science, time to new business functionality is accelerated by that much. This process is highly iterative, and this is what does it.